Did you know that a t-test, correlation, regression, and ANOVA, at least for a basic problem, have results that are mathematically identical? When first learning about statistics, there are an incredible number of tests to learn. Many have the names of long-dead statisticians such as Bayes, Pearson, Fisher, and Bonferroni. There are many fundamental concepts and mathematics, however, underpinning many techniques, particularly the most popular ones. If you have a problem that could be tackled with the t-test, did you know that you could use a correlation, regression, or ANOVA procedure to get the same result? In fact, correlation, regression, and ANOVA can be seen as generalizations of the humble t-test. That is, they can do a t-test, but they can also tackle more complex problems. So to demonstrate this equivalence, I'll use a simple example. Let's say a drug company wants to know if drug 1 or drug 2 is better at controlling diastolic blood pressure. The company chooses 10 people with equally high blood pressure and measures BP after a month on either drug 1 or drug 2. Here's our example in SPSS. We have 3 columns: the patient, name in the first column, drug in the second column, and blood pressure. Here we're using diastolic blood pressure just for simplicity. I'm going to analyze this first using a t-test. So I'm going to go to Analyze, Compare Means, Independent Samples t-test. Now our outcome is going to be the blood pressure, and our drug is going to be the grouping variable that we have. And in our data set, we define them as drug 1 and drug 2. And then I'm going to click on OK to get the results. Here you can see drug 1 and drug 2 had a different mean blood pressure. And in fact, drug 1 had a lower mean blood pressure, which is presumably the better drug than drug 2. But the key that we want to look at is this independent samples t-test. And here we're looking at this probability level here, which is less than 0.05. And we're going to use that as the criteria for whether something's significant or not. Sometimes it's lower, sometimes it's 0.01, or even lower still, depending on the application. But we're just going to say 0.05 is our standard for what's significant or not. And so in this case, this 0.015 is in fact below 0.05. Therefore, we can declare that there's a significant difference between these two means. And in fact, drug 1 is superior to drug 2 in producing lower blood pressure. But the key here is we want to look at this probability level, because this is saying whether there is a difference between the two drugs. I'm going to show that in using other techniques, we're going to find the same result. So here I'm not going to save that, but I'm going to go on to the next technique. So the next technique that I'm going to use is to analyze this with a correlation. So I'm going to go correlate, bivariate, and then I'm going to enter drug and also blood pressure to see the relationship between the two. I'm using Pearson correlation two-tailed test, and then I'm going to click OK, and the results come up on this screen. And here, in fact, there is a positive correlation between the drug and blood pressure. That's 0.3739. The little star shows that it's significant, but you'll notice it also gives the probability value. And look, this is the exact same probability that there was before, 0.015. So this positive correlation, remember, drug 2 was associated with higher blood pressure, drug 1 with lower blood pressure, and therefore that's why this is a positive correlation, because this is showing some additional information and showing the strength of the relationship between the two variables, a relatively strong relationship. But again, the key here is we're looking at this probability value. It's less than 0.05, and in fact, it's exactly the same probability that we found before, because again, for this example, it's the same result. It's showing that there is a relationship between the drug you take and the blood pressure that you ultimately get. So now let's look at this next with regression. So I'm going to go Analyze, Regression, and I'm going to go Linear Regression. And I get this dialog here that doesn't fit very well on the screen, but nevertheless, we're going to say the dependent variable, the outcome is going to be blood pressure, and the independent variable is going to be drug. And then I'll just click OK again and look at the output here. Here's the output. Again, it's showing the model R squared, or R rather, which is exactly the same as the correlation that we found before, or very close to. And then we're going down and we're finding the significance. And again, right here, 0.015, that's showing the significant association between the drug and what drug you take and what outcome you actually get. So again, the same result. Now we're going to go and look at ANOVA. And so here we're going to compare means. We're going to go to one-way ANOVA. And we're going to put in the dependent variable, the outcome list, the blood pressure. And we're going to put as the independent factor, the drug. And we're going to click OK. And here's the result. And again, looking at the significant relationship between the two, the probability level is 0.015, which is exactly what we found in our prior example. Well, there you have it. Each statistical test looks at whether there is a significant relationship between two variables, in our case, drug and blood pressure. Consequently, it should not be too surprising that different statistical procedures should produce the same results. Some of the mathematical and conceptual underpinnings are the same. Thank you for watching.